Thanks, everyone. So my name's Scott. This is David. We're going to be giving a talk today about event sourcing with Event Store. As a quick agenda, we have an introduction. We'll just introduce ourselves and our experience on the topic. David's then going to talk, I'm going to provide a bit of a background for event sourcing. What is event sourcing? What is Event Store? David will talk about designing and handling events. I'll have some comments on a couple of different architecture patterns or trade-offs that have come up. And we'll have a quick summary. We have about 6 bullet points you can take home to your manager. And then we have some time for some questions at the end. If you do have questions throughout on topics of clarification, if something's confusing, feel free to put your hand up and ask. But we'd like to keep discussion or more in-depth comment or questions to the end. For background, I've been working with event sourcing and Event Store in particular for the last 2 years. Before that, I came from a more traditional relational database background. All of this is within the web application development space, and mostly with Java or other similar languages, C#, things like that.
Now, for myself, have fairly similar experience. I've been working in software for about 5 years now, and before this, I was developing a monolithic application using a relational database. About 1.5 years now, doing event sourcing.
So a little bit of context on the project. The project we're working on is called Polaris, and the company we're at is Synopsys. The Polaris project itself is a software as a service product, targeting mostly large enterprise clients. And the domain is automatic detection of security and quality defects. So we do things like static code analysis, bill of materials, interactive security testing, fuzz testing, things like that. And in particular, the Polaris project is aggregating, reporting on, and monitoring these issues over time. So over the lifetime of multiple scans of your application, not within an individual scan. The current implementation is approximately 20 to 30 different unique services with replication factors that seem to range from 1 to 5. Just to give you a feel of the scale of our web applications, I'll let you decide whether this is microservices or not. I tend to just say multi-service. Code languages, at least on the server side, are mostly Java and Go. Data persistence, Event Store, Postgres, Mongo, and Consul. And SIG, the software integrity group at Synopsys, is just the software analysis team. Synopsys also does a bunch of hardware design, analysis, and testing. Event sourcing and Event Store. Event sourcing is a data persistence pattern. You could say it's on par with relational databases, document databases. These are things that have multiple different implementations. And then Event Store is perhaps the canonical, or is certainly a implementation of event sourcing, in the same way that Postgres is an implementation of a relational database. We use ESJC, which is a third-party JVM client for most of our interaction with Event Store. Event Store provides REST and TCP APIs, so if you want to interact with it at that level, you can. Most of our code that interacts with Event Store is written in Java, and so it is also, or is just using ESJC. Event Store itself is open source, and we actually are in the process of committing back to it or fixing a null pointer that we've identified in it. A little bit of motivation. Why are we working with event sourcing and Event Store? We were given the mandate with this project to be a bit more experimental. The Polaris project is, while also working as a platform, which is a new feature, you could say, we're also expected to experiment and try and push beyond the default implementation options to see if there are some different ways of addressing some of the scaling and performance issues or concerns from previous implementations. So this is a greenfield rebuild of an existing project, adding both features and exploring alternate architectural options. In particular, we were interested in some of the things that are proposed by event sourcing, so keeping a full history of changes instead of just the latest state. For example, allowing for a full audit of the state of the system at times in the past, allowing us to do analytics over time. And also the enforced separation of concerns between reading and writing of data. So you might have heard of this as CQRS, or just read-write segregation. And I'll talk about that at the end of the talk a little bit. Event Store itself, as I said, it's open source. It is custom built for the event sourcing pattern. You can sort of tell by the name. They're very focused on this. You could set up an event sourcing pattern with Kafka or some other tooling. You could set it up with Postgres if you wanted to. You can build anything from scratch. But it's opinionated and focused. So we decided to go with Event Store and see how that would pan out. Some terminology that we'll be using, both vocabulary and then sort of visual iconography that we'll be using throughout the talk. An event is a single document or record written to Event Store, or a message if you're used to message queuing services. A stream is an append-only list of events. Event Store itself is just a collection of streams. It also comes with some niceties that it can add on top of this, but we won't go into any of the details there. A publisher is an application component that appends events to a stream. It writes events. This is your data write side, while a subscriber is an application component that reads events from a stream. These components, they could be processes, they could be threads, they could be web services. In our case, they're web services. They happen to be running as Docker images in Kubernetes, but that's sort of beside the point. A projection is a view or a subset or a transformed subset of the events or of the data in a stream. And we'll come back to this in a bit, but usually a projection is, at least in our case, it's a different data store. So we might use Postgres or in-memory maps or Mongo to store a subset of the data in a stream. And the terminology we use around that is we have a subscriber that subscribes to the stream and generates a projection that is used to handle queries. Apologies to the domain-driven design folk. We're going to be a bit fuzzy or loose about our use of the term entity. You could, if you're being pedantic, say entity aggregate. We're just going to say entity. And this could be a class or a table in a relational database if that's what you're used to. Visually, an event is a little block. We'll have a stream of events. They might be numbered. We have arrows for publishing, subscribing, or reading and writing. And then our classic cylinder for a database. As a quick example, just using this iconography, we have a publisher service. It is writing events to an event stream. And then we have a second service that is subscribing, and it is projecting into a database. This could be Postgres or Mongo. How are we doing for time? Okay, David.
Oh, hopefully this works. Can you guys hear me? Fine? Yeah. Okay, so first I want to describe a user object. We'll be using this throughout the presentation or referencing it. We have 4 fields on this entity. We have a UUID, which is just a unique identifier, a name, which is not empty, email, which needs to be well-formed and unique, and then also a group, which is an entity relation. And this is how it may look like in a table, in a relational database. How do we write events for these entities? I like to think of following 3 basic principles when coming up with an event to describe an entity and its change of status throughout time. An event should be very descriptive of a single action on the entity. Pretty important to be able to, at a glance, see what is happening in your system. Should only contain the necessary data, beyond just being able to know what you're supposed to be acting on in the event, you also have to consider data storage as well, because these events are going to live on forever. This is a immutable data store that has an infinite retention policy unless you set up your own sort of archival strategy. And then also, it has to have valid data. We'll talk a bit more about that later, but data validation is very important. And I'm going to quickly run through a few examples here of events. User creation, user email updating, which is just a field update, and then how to assign entity relations. So here we can see that Event Store stores everything in the JSON format, or at least presents it to you that way. And you're given 2 fields to populate. Data is going to be the information that you care about in the event that the subscribers are going to process. But you also are provided this metadata field. And this is useful for things like serialization into a Java domain object. And also, if you want to add some things like timestamps in order to troubleshoot issues and see when an event was created in your system. And the events are pretty simple. We can see that we have 3 fields here, and they all pass our validation checks. It's a UUID in the ID field, a non-empty name, and a well-formed email. Moving on to an update event, very much the same. Notice there's a different event type. This is important because sometimes you'll have events that have similar data. So having different event types allows you to know what action is taking place. And we don't have the fields that aren't being operated on, like the name and the group. And then representing relational data is pretty simple too. Just a couple primary keys and foreign keys. And it's the responsibility of the publisher to validate this data. Because as you can imagine, the event store doesn't have any concept of relations. It's not going to maintain that referential integrity for you. So we do have a few tricks in store for how to manage that. And here's a representation that you might see of user or group streams. You can have multiple streams. You can choose the granularity of the streams that you want. You could have your whole application using a single stream with every entity just being placed in there if you choose so. We'll talk a bit more about that later. But in this case, we have a couple streams, the user and group stream. They're sequential, read left to right, user creation, user email updated, user group assigned. And these streams don't have to be, they don't necessarily match up. The group stream position 0 wasn't necessarily created at the same time as the user stream at position 0. So that is to say they're independent of one another. And there are some instances of bad events, or at least what we believe are bad events. In particular, having events that are too generic. This is problematic in that you can't really tell what you're supposed to be doing or what your system's doing, what action is taking place. A generic user updated event, anything could be updated, so you have to dive into the event itself to figure out what was updated, and maybe even reference old states of the entity that you're operating on in order to figure out what was updated. So even though it seems a bit cumbersome to write more events, in the long run it's actually better, and we'll get into that a bit more as well. And invalid data. Being that it's an immutable data store, it's not simple to modify or delete this data or update it in any way. So you have to be sure that everything you're placing on that stream is valid. It's particularly harmful if you produce an exceptional state in your subscriber. So if you're listening, you try and insert into a database, it throws a constraint violation or a foreign key exception. How do you handle that? Typically, you just have a service failure, and you have to either skip over that event, which is a bad thing to do because now you aren't familiar with the state of the system, or you never can't trust the state of the system. Valid data. Okay, yeah. So exceptional state, you stop processing the events, or you skip over the event and you can't trust the state of the system. The user may keep trying to send the same data. Overall, it's pretty bad. So ways to avoid this is field validation at write time. This is pretty simple. If you have a not empty or not null value or a particular data format that you're expecting, you can just use Java Bean validation. So in this code here, it's just a wrapper abstract class that you could put around entity or an event to ensure that every time you write an event that you validate or put it through the Java Bean validation. But for more complex scenarios, such as database constraints, index violations like unique or foreign key constraints, referential integrity, and the like, you're going to want to append or write to a known stream position. So if you take the current stream position and then also get the state of your application at that time, represented here by that event store get stream position, and then using a data access object to get this reference, you can be sure that if you can write to that stream position, that you have that referential integrity in place. You don't have to worry about issues on the subscriber side of things. But as your application grows and you get more and more publishers, you can start having write contention. So if you do have different publishers colliding with one another, you can go through the process of having continuously reprocessing the event, or you could reject the event, which is a bad user experience. And another option is to segment your streams, get them to be more granular, which is something Scott will talk about a bit more later. So what is the result of writing good events? I think the primary thing is it's easy to troubleshoot when issues arise in your system. It's easy to know the state of the system. If you have those granular events, at a glance, when you look at the list of events that have taken place within say a certain period of time that you know this error happened in your system, you can see at a glance what happened. But then you can also have another service subscribe to your stream, which is pretty powerful too. Like take this diagram I have here. So we have this user stream and a user subscriber, which creates a view of the users, regular user service stuff. But let's say that you have another notification service. This service wants to send out emails to these users for whatever reason. Instead of having this service cross the service boundary, have to make requests to this user service in order to get the email and send it out, there's going to be a delay there. Instead, the notification subscriber points to or grabs events from the user stream and builds up its own model of these users, and it can reference it with its own data access layer. So in this case, your traditional database is now a view or a read view. And this is very useful in that you can use the right data store for your domain. In a multi-service application, you can have many services that maybe it makes sense to use a document store, a graph database, or a traditional relational database. You have that flexibility for every service to choose its own way to represent the data that it cares about without having to do some interesting transformation of data maybe through a script or something. Yeah, so changing the view doesn't require complex scripts. You just apply functions to the events in order to represent that data or project that data into another data store, like Postgres. So we recently benefited from this. Again, because it is a greenfield project, we tried out document store. So we tried out Mongo. We thought it would be interesting, or it's supposed to be web scale. It's supposed to be fast. But we found that we have relational data and we like ACID transactions, so we wanted to move over to Postgres. And this was a relatively simple process. It only took, I think, a few weeks of time just to write the different data access layers, these plugins to talk to Postgres, and then different event handlers, so that this new version of the service, when it got deployed, all it had to do was read from the event store, and then apply those event handling functions in order to populate the Postgres database. And this means we avoided doing some crazy migration scripts, or writing some SQL, or exporting the database and then doing weird, crazy data transformation. I know in my past job, when I worked on that monolithic web application with a relational database, we did have to do some database migrations, and this caused, we had to have service outages for an afternoon up to a whole weekend in order to do these crazy things that I think can be avoided with event sourcing, and this seems like a really powerful tool for that. So going from an entire weekend, we did this data migration in about 10 to 15 minutes of downtime. But that's because we didn't have the proper deployments in place. So if we got to full blue-green deployments, then we could get down to virtually zero downtime and no noticeable impact on the users. Which is, I think that's really useful for experimentation or finding the right database or data store for you to use. Eventually over time your requirements may change, and what made sense to be Mongo now makes sense to be Postgres, and that's just, it's a really powerful thing to have. But this comes at a trade-off. When you have events as the source of truth, you now have introduced another technology to your architecture stack that you have to account for. You have to account for it both in terms of data integrity, but also in terms of development. Now developers have to know, how do I write to the event store? And then also, how do I write to the projected data stores, so Postgres or Mongo? And then also, during troubleshooting issues, you have to check the event store. Now, again, just another thing to check, like, is the publisher writing events? Are those events valid? Okay, they are. Then is the subscriber processing events, and is it caught up? Because typically in the event sourcing model, a subscriber will start from the beginning of time in order to populate the database to a known point. And because it's something new, you also have to, you may get into a situation where you follow patterns that don't make sense or that are problematic, but don't really arise until a later time. So when we first started off, a lot of our services weren't replicated. In development environments, we only needed one instance of a service. So a developer could go about doing something like having a subscriber have both subscription and publish responsibilities. So it'd read, like, let's say in this example, the third event, it realizes that, not really sure of a concrete example here, but the basic idea that this event causes the subscriber to emit another event onto that same stream. And as long as your application has a long uptime, and you only have one replica, this won't come up until later. We call this doing derived events. And it's problematic because it's difficult to find the source of the event. If you have this long chain of subscribers emitting events over and over and over again, where did it start? And then even more problematic is reprocessing the event stream. So say you bring up another replica, you're horizontally scaling and it's reading from the beginning, it's going to duplicate the event, and now you're in an inconsistent state or in a bad state in your system because potentially you created two of the same users. So instead, create all events at the source whenever you're publishing. If you know that you have to have multiple actions take place, just do it right at the source, write multiple events if need be. And then eventually in your system, you're going to have bad data. Bugs are going to come up. It just happens. Edge cases aren't caught. And this is pretty difficult given that it's an immutable data store. It's not really apparent what you can do at first. I mean, going from a relational database background, you may think that, oh, okay, given that I have this test account email that has some, weird encoding, I could just update that event, or I could potentially delete that event. But you can't, it's immutable. And even if you could, at that point in time, you need to tell all of your subscribers that it needs to reprocess the entire event stream in order to pick up that new data. And it would actually have to wipe out its current view and rebuild it from scratch. So that's not what we want to do. Instead, we want to apply corrective events. And the first step in that is fixing the publisher. So if you ever catch an edge case, make sure that you fix the issue at the source, write some unit and integration tests. And then after that, you can create a run once subscriber publisher that applies a fix. So in this case, it would read that third event and then write a corrective event that updates the email to the correct form. This is an example of the derived events, but this is a special case in that we need to correct the underlying data. And then another case that we came upon was legal came up to us and said GDPR now means individual users have to or are allowed to request deletion of their data. And we started off with this one stream of users. It's like, oh, well, that's not good because if you delete this stream, you delete all user streams. So in that case, we had to segment the streams. Now, every user has its own stream of data. And the way to do this, you have to write some sort of migration service that can read the stream, emit new streams, and then also notify the subscribers that they need to update their reference to the new streams that have been emitted or deploy a new subscriber that points to those new streams. All right, and with that, I'll hand it over to Scott.
Thanks, David. So David was just talking about data migration and moving from a single stream for all users or all of your instances of an entity to separate streams per instance of an entity. And that brings up the question of what is the correct granularity of your streams? This is something that's not always obvious up front, just like when you're designing your entities in a traditional system. And so you start somewhere, and that's what we did. We started somewhere. We ended up starting at the left-hand side of this spectrum. So we started out with a single stream for all users. And then as time went on, we realized that we needed to at least be able to delete data at the tenant level. So we started by organization. And then with supporting GDPR, we need to be able to do it at the individual user level. And that's sort of the initial justification for why we moved down to the entity level for streams. There are some trade-offs with this. So on the left-hand side of the spectrum, you have fewer streams. It's almost a fixed number up front, whereas on the right-hand side, you have more streams, and it scales with the number of entities, the number of users. Event Store claims support up to millions of streams. That matches what we've been observing so far. We haven't pushed beyond that in production. The problem with the right-hand side of the spectrum is that you don't get coordination of timing. So you can put a timestamp on events, and if you have a single system or a single service generating those timestamps, then and the clock is constant, the clock doesn't go through any sort of shifts, or the service isn't restarted, that should be okay. But if you have multiple services distributed across data centers and maybe the clock synchronization doesn't keep up, or a subscriber just publishes bad data, by the time the event gets published, it's out of date. So you can't always rely on the timestamp in the metadata of an event. And so by putting all events into a single stream, you get a strong ordering. So you know that this event happened before or after any other event in that stream. And that's true for all events within a given stream, but it's not true for events across streams. It's kind of like when you have a team and you distribute them over multiple code repos. A commit, if you have a single mono repo and someone makes a commit, then you know that it happened before or after any other commit in that branch. If you have multiple repos, there's no enforced coordination there. So positives for the right-hand side, you get reduced write contention, and you also get this deletion benefit. Positives for the left-hand side, you get better coordination. The takeaway from this for us is just we started out at the left-hand side, we ended up moving towards the right-hand side. The second topic I'm going to talk about, I'm going to try and cover three things here, sort of at the architectural level. The second one is the two different types of subscriptions. Event Store itself supports two types of subscriptions. You can come up with other ones, but in practice we use two of them. The first one is catch-up subscriptions, meaning when you start this subscription, or if you restart it, or if another instance starts with a copy of this subscription, it will start from the beginning of time on the stream that it's subscribing to. It'll start from event 0 and then process through to the current event. I think this is the one animation we have in here. The second type of subscription is a live-only subscription. And so this is something where there's an existing stream, there's existing events on the stream, and a subscriber says, okay, I'm interested in new events. I don't want to worry about the existing ones, just tell me about the new ones. There we go, we have two animations. If you only have live-only subscriptions in your system, then you don't need event sourcing. This just devolves down to a message bus, a message queue, whatever your terminology is. Use RabbitMQ, use Kafka, something like that. As soon as you have catch-up subscriptions or believe that you will be interested in that data, the past data or past states of the application in the future, that's where the addition of the event sourcing, the immutable log, where you're keeping all of the data, comes into play.
So Event Store actually saves the data in a database somewhere?
Yes, yeah. Yes, yeah. Internally to files, and it's not wrapping Postgres as far as we know, or Mongo or any other known technology. It's built from the ground up to disk, yeah.
So it's like replicated sharing solution. You have to back up the disk for all the servers?
It is. It comes with replication built in, so in production we'll run on the order of 3 to 5 currently replicas of Event Store.
And then your probe is still taking the backup?
And we do. You should actually ask our DevOps team whether what their process for backing up that data is. One way of thinking about event sourcing is that it is a message bus. or message queue with persistence of all messages. So event sourcing is just RabbitMQ, where you've added a subscriber that writes everything out to disk, and if someone wants to, they can go back to the beginning of time and reprocess all of those events. So CQRS, this is the third pattern I'm going to talk about, and I promised I'd get to this at the beginning of the talk. As a little bit of background, CQRS stands for Command Query Responsibility Segregation. Here we have it set up without event sourcing. I'll add in event sourcing in a little bit. We have an API consumer on the left, and they write data to a command service, which writes data to your data store. If they're interested in reading data, that goes to a separate service, a separate implementation. Again, it could be a separate process, it could be a separate thread, it could be, as in our case, a separate web service. Why would you do this? It adds complexity. It simplifies the responsibility within a service, but over the entire system, it adds complexity. It allows for horizontal scaling of individual components, though, which is nice. So if you have a read-heavy system, you can horizontally replicate the query service. It's not responsible for writing data, so you haven't had to deal with any sort of leader election or write contention yet. And if a single instance of your command service handles all your writes, you're happy. Here I've just put in an event stream instead of the data store. Moved it over a little bit. And now we're getting the benefits of using Event Store. We've added in another analytics service. It's interested in looking at counts of users over time, maybe charting that, maybe suggesting what changes could be done to support user growth. But so far, we haven't got any benefit from the combination of CQRS and event sourcing. This is just, we have CQRS, we can horizontally scale the query service, we can add other subscribers as necessary. If we zoom in on the subscribers of this, we'll get two subscribers, subscriber A and subscriber B. They're both subscribing to the events of the same stream. What I've added here is that there's two little icons for individual databases or data stores for each of the subscribers. Now each of the subscribers is able to optimize for its own query patterns. It's able to use a database or even just a schema that's more relevant to what it's interested in. And one of them going down doesn't necessarily take down the other one. So the takeaway here, or the overarching benefit of this architecture is you write once to a single source of truth. This means that you have to have your command handlers do their validation based off of the existing events in the system. You may or may not have to horizontally scale them. If you do, then you have to add coordination amongst them. But once information is published to the event stream, that is your source of truth. And you can add as many subscribers as you want, which can each have their own view of the world that is useful for answering the question that subscriber is interested in answering. Fairly important note, this system is only eventually consistent. If one subscriber takes longer than the other, if one of them goes down temporarily, if you ask both of them, say, what's the total number of users in the system, you might get different answers back. So, trade-offs. Here we have a summary. David talked about designing and handling events. So the 3 takeaway points for that are, be careful what you event. This is a change from what you might be used to. Events are the source of truth. Everything else, you can throw it away, you can regenerate it. Don't assume that just because your projection is correct or incorrect, that the data that matters is correct or incorrect. Data migration, try and avoid it, but at some point you're going to have to do it. Again, it is somewhat different from what you'd expect from a current state only database, something that just stores the current state of the system. Architectural patterns that are of interest or that are worth keeping an eye on. Figure out your stream scoping. Start simple, but aim for the entity level streams. This allows for things like removal of data at the entity level. Live-only subscriptions, if you do have a system that purely has live-only subscriptions, don't worry about event sourcing, just use a message queue. And then CQRS and event sourcing, at least in our case and for the project that we're working on, has worked well and allows for the independent scaling of responsibilities, which is what we were expected and what we were looking for. And then just a final bonus one, trying new patterns is valuable. We had fun, we learned a lot from this. I would take a lot out of this even if I went back to a regular Postgres or Mongo or one data store only system, just in the design of how, just in the options that are available and how I interact with data. The same way that doing a bit of functional programming or logic programming might influence how you write a more traditional programming language. But it does take some time and effort. I believe the slides will be shared. We have a couple of additional resources, links to Event Store itself. We have a requisite Martin Fowler link, because everyone has to have that in their presentation. And then a couple of good articles which, although they don't mention event sourcing in particular, this first one by LinkedIn talks about the log as the source of truth. And then the second one from the Confluent blog just talks about messaging as a single source of truth. Very similar concepts, lots of overlap, worth checking out. So I think we'll open it up for questions now. Again, we work at Synopsys. We're based in downtown Calgary. Our branch office is in downtown Calgary. Come visit us anytime. And how are we doing for time? I have a bit of bonus content, but let's start with questions.
So your subscribers, do they typically store data or do they different kind of stuff storing the data?
So you're asking if the subscribers persist data, yeah. So most of our subscribers have some sort of data persistence. Some of them only persist data in memory, if that's sort of what you're asking.
So like the requirement, or I guess the feature,
Mhm.
that you have a single source of truth, that's sort of point about it. Was that required by the business or the like a technical nice to have?
Technical, I think.
Like,
It would depend on who you ask for. There's not a regulatory requirement. We're not a regulated industry. We're not healthcare. We're not finance.
So how do you deal with cases when you have a single source of truth, but let's say there's the same entity being updated by two different browser windows or whatever,
Right.
and the write gets committed, but then it fails because one of the override.
So you definitely have multiple writer problems. And if you need multiple writers if you need to block that, if you need to coordinate, basically, then you need to have what you want to coordinate on a single stream. So anything that you need to coordinate, anything that you want to block.
No, you're not a single stream. So let's have two different screens. It's kind of simplified. Two different screens where I assign the user to, and one person is assigning the user to group A, another person is assigning to group B, but the user can be asking the same.
So that's addressed with writing to a known position. So if you have a bunch of events that don't need to be coordinated and happen to be on the same stream, then you don't need to validate them. You just keep writing them. Maybe you have a bunch of sensors that are writing. If you want them to coordinate, then you need to, the thing that does the publication of the event needs to first subscribe, catch up to a point. It catches up to point X. It believes that's the most recent, or event X. And then it says, OK, in all of the events I've seen, I haven't seen one that conflicts with it. I will now write a new event, and it should be at X plus 1. And that's a request to Event Store to write this new event at position X plus 1, and send me back an error if someone has already written to X plus 1. So we have two people that have subscribed and caught up to X. They both want to write conflicting events to position X plus 1. One of them will get in, and one of them will be rejected. And that's just like...
So, I mean, this is sort of traditional concept of pessimistic concurrency.
Yes. Yeah.
In a way, it's a sort of a poor form of concurrency.
Yeah. Yeah. No, anything that needs to be, I use coordination, but that has to be locked or concurrent needs to be on the same stream, and you need to apply this pattern here.
What about the backup and recovery? Like, does this event store provide like a mechanism for in case something fails, like mid-write or something?
Failing mid-write, I don't know how that's handled. My assumption is that writing, as far as event store is concerned, is atomic. Right? So if you're writing an event to a stream, it will either be written or not. If you wanted to go and write a manual backup with rsync, there's a bunch of files in the event store service that you can copy out and copy into place into another one, and it will pick up from the state of those files. If you copied that in the middle of a write, my understanding, although I haven't actually tested it, would be that it would just drop that last partially written one. The other pattern that you could use is just you add a subscriber, and that is your backup. You write to something else. Right? So you subscribe to a stream, and everything that subscriber sees, it writes to wherever you want to back that up. That could be offsite or just another database, or that makes sense.
Recovery would be just
Replay those events back into the system, yeah. So you could always write the events out to your own file format somewhere, and then regurgitate them back in to a new instance if you wanted. Okay. Any other questions?
So you use an example of changing an email as an email updated. Is there a lower limit where you would stop making messages? Would you change your first name, change last name,
Suggesting it's too small. It's too small.
Sure. I don't think anything's too granular. I would do it on a per field basis, personally. It seems a bit unwieldy or a bit much, but one of the nice things as you get down to a granularity level of per field, anyone who looks at the list of events can know exactly what happens in your system. It can infer the business logic, and it wouldn't another subscribing service wouldn't have to reference your lengthy documentation in order to understand the system. So those events essentially become an API into your own system without having to delve into documentation to figure out the exact business logic that takes place. You know, for instance, what if you don't update the ID on a field, so you will never have a user ID updated event. But if it's just a granular or regular user update event, you don't know that. You could potentially group things together. Maybe, name is in 3 different fields, but if you want to group them together, maybe that would be all right. But it's kind of up to you. I personally prefer field granularity. I like the benefits that gives you.
The thing I might add to that is just that it's kind of like your domain-driven design, entity design problem. What is a meaningful operation? The goal with event sourcing is to have events that are somewhat meaningful to the business. And so it takes a bit of practice, and it depends on your domain.
So, honestly, if you're the business system, you feel it's
In our case, it seems to be working, and it seems to be. We haven't done a proper experiment where we've gone and done exact implementations of the same feature set in 2 different ways.
So I feel like if there's a failure of storage, then that becomes a problem.
haven't
So-
had to look into that yet, but there is there is the concept of archiving your data and even creating a snapshot within the event store itself. So that snapshot would be from a point in time forward. We haven't looked into that because, we're a fairly recent project. We haven't had to kind of cull that data yet, but they have thought about it. They do talk about, like the people at Event Store do talk about some other systems that do have quite large amounts of data, and it works well for them. They can process the events quite quickly. But yeah, I guess, you're in operation for 20 years. Eventually that old data isn't really relevant anymore. Maybe just archive it somewhere, take a snapshot, and then continue on from that point.
One of the benefits that we believe will come from splitting out so that we don't have a stream per domain, either by having a stream per client organization or a stream per entity or entity aggregate, is that then you can have a subscriber that's only interested in a subset of the entities or a subset of the clients. And you get to shard across, across tenant or across entity. So if you're unable to apply enough compute capacity across the entire system in a single instance of a processor, you can then allocate different streams to different instances of the processor, and then that gives you. Sorry? Yes, yeah. The majority of my initial development work was regularly replaying data, but it's not a particularly useful answer without, say, a number of events in those streams. Mm-hmm.
Can we ever get rid of the process? Yeah. Like the process of running it, right?
So Event Store itself supports deletion at the stream level, and the expectation being that subscribers will understand that a stream might no longer exist. But an individual event, if you want to, say we had 1 million long stream of events, and you want to delete the first one because you accidentally put your password in it. It's kind of the same as when you're doing something like that with Git. If you have a Git repo where the first commit introduced a secret or a password, and then you've got 1 million commits on top. Yeah.
Regulations change after that kick.
Mhm.
That's required. You want to track every change that you want.
No, and so it depends on.
Maybe it adds a lot of constraint to it.
No, just like anything, if you're depending on the domain or your interests, those requirements will change. And it definitely is a set of trade-offs. If you're interested in that audit history, that log, the past states of the system, then they're going to come with some costs that are not present in a system that only maintains the current state. The worst case scenario for deleting that first event in 1 million events is to just create a subscriber that skips the first event and then reads every other event and writes it out to a new stream. So we assume compute is infinite until we run into problems. Cool. Thanks, everyone.